So in one of my other lectures, I talked about growth curves and setting up the growth curve. And a lot of times that understanding a trajectory of a phenomenon is substantive enough that we might publish that. But most of the time, actually, we want to understand a trajectory, and then we want to understand what might influence where people start on that trajectory, their intercept, and their rate of change or their slope. And so today I'm going to talk about some additions to the general growth curve by adding time-varying covariates and time-invariant covariates. So sometimes we have measures of our covariates only at one time point, say at baseline, and other times, or we're just interested in the effects of those at baseline. And other times we have a covariate measured across time at the same time point, say, as the measures in a growth curve. And we can actually, depending on our research hypotheses, predict either where we're using a predictor to predict a rate of change into the future or trajectory into the future, or sometimes we have the idea that there is a concurrent association where we might be more interested in what are called time-varying covariates. So I'm going to show how to do that and how to interpret those, and then also look at a lot of times when we have family data, we have growth curves, say, from a husband and a wife, or from parents and a child, or multiple siblings, or something like that. And so we sometimes want to model multiple trajectories together, or using multiple groups, and then we want to test constraints across groups, and so forth. So those are the things I'm going to talk about today. Okay, I just mentioned time-invariant predictors that do not change across time. That is, whatever their value is at the first time point, it stays that same value, like gender. SES variables sometimes, like education level among older adults, probably isn't going to change much. Number of children, things like that. Let's see. So when our growth curve intercept variance parameter is statistically significant using that Wald test, when there's variation there or variation in the slope, then we can add predictors and account for some of that variation. And in SEM, we can actually request an R-square for our latent variable of intercept and our latent slope to know how much variation is accounted for in our model, which is kind of a nice feature. In terms of interpreting, these are results from a growth curve of child internalizing behavior, where we see an intercept of 1.59, so let's say starting about right here, and then a downward slope of 0.46. So for every 1 unit change in time, the average level goes down by 0.46. And then we have a quadratic slope that's positive, suggesting kind of an uptick at the end of the curve. However, it's not statistically different from zero. Yet when we look at the variance parameters, we have significant variation around the intercept, significant around the slope, and a significant amount of variation around the quadratic slope, even though that slope is not different from zero, the average slope. So it's a good idea to look at our plots of our data, our spaghetti plots, and see, okay, does this variance around the intercept make sense? Variance around the slope, could there be variance around maybe a quadratic effect there? And so that's something that we might want to look at. Because they're significant variance parameters, we can predict each of these, even though the quadratic slope is not, the average is not different from zero. So here I have some output from the intercept is 1.59, and we could say that the mother's level of warmth has a non-significant association. The husband's warmth, if the husband's warm, then the intercept is lower by 0.12. I guess I have the interpretation there. A 1 unit increase in husband warmth is linked with a 0.12 decrease in the initial level of child internalizing. So if the father's warm, then the child's going to start with less internalizing. Then if we look at predictors of our slope, now remember our slope is a downward slope, okay? And husband warmth, again, has a significant positive association. So the way we interpret that 0.071 coefficient is a 1 unit increase in husband warmth is linked with a 0.07 increase, so the slope becomes less steep in the rate of change of child internalizing. So it goes from a negative 0.46 to a negative 0.39. And we also have husband's warmth has a significant predictor of the quadratic slope, where if the quadratic slope is 0.36, a 1 unit increase in husband warmth is linked with a 0.01 decrease in the rate of change of the slope of child internalizing. So let me just mention, so our intercept is where we start, our slope is our rate of change, and our quadratic slope is our change in our rate of change. And so, so this predictor of the quadratic slope is a decrease in the rate of change. A decrease in the change in rate of change. It's really what that should read. So they get tricky when we start to talk about how do we interpret a quadratic slope. So my suggestion is that you find a published article that predicts quadratic slopes and see how they've talked about it, where reviewers and editors have been helpful in wording and try and use that wording. Sometimes we want to model 2, 3, or more simultaneous growth curves. And sometimes when we do this, we will correlate intercepts, correlate slopes. We can even use intercepts in one person to predict slopes in another person. There are a number of variations of longitudinal analysis across multiple people. One of those is called a factor of curves, where we have multiple curves for multiple people, and then we take a factor analysis of those curves. Another variation of this is called the curve of factors model, where we have a number of factors at a given time point, and then we do a growth curve across factors, and I'll show an example of that here in a minute. The ALT model is another example where we have simultaneous growth curves where we correlate intercepts and slopes, but also include a cross lag where intercepts predict slopes, like I mentioned this before. Actually, so that's one variation. The ALT model has, like, if you put the intercept and slope for the husband up here with the observed variables for that slope down here, and for the wife you've got the intercept and slope down here and the observed variables in the middle. So in the middle we have our observed variables. We could say wife predicts husbands at time 2, wife 1 predicts husbands at time 2, wife's time 2 variable predicts husband's time 3 variable, and then we see that going in the other direction as well. So that's where we get the cross lag effect going on. There are, again, a lot of variations. Let me show you a few. Okay, so say we're looking at substance use. This is actually from the Duncan and Stryker book. I should have that reference here, but this is Duncan and Stryker, where we have a common factor at time 1 of, say, alcohol. Let's see, my next slide tells me exactly what this is. Alcohol, tobacco, marijuana. So here at time 1, we have alcohol use, tobacco use, and marijuana use at time 1. And at time 2, we have alcohol, marijuana, tobacco, at time 3, and at time 4, the same thing. And then we have a curve. So this is basically another way to talk about this. This is a latent variable growth curve, a growth curve of latent variables. And then we have a factor of curves, which is a different approach where we could say, I'm going to take a common intercept from an alcohol intercept and slope, so I have a common intercept and a common slope for alcohol growth curve, tobacco growth curve, and marijuana growth curve. Now, some caution with these models, because of their complexity, require some additional constraints. The second order loadings need to be set across the intercept and slope. The first order latent means need to be set at 0. For the curve of factor model, we have to have factor loadings, intercept, and error variances equal across time, and the mean set at 0, the latent mean set at 0. Here's some references where you could find more information about these models. There aren't many situations of these models where they're actually published for a specific view of the content, but rather they're methodological papers mainly. So those are some options. We could fit dual growth curves within the same model. We can also fit dual growth curves across different groups. So boys and girls, husbands and wives. I guess for husbands and wives, we would want them in the same group because we want to correlate them because they're not independent of each other. However, for something that's boys and girls that are not siblings, we might have a boy group and a girl group, or across race groups or other moderators like that. Let's see. Talked about the variance parameters already. And I've already talked about the associative latent growth model is where we combine growth curves in the same group in the same model. Okay, so here are some examples. Cui and Donnellan published looking at, first over here on the left side we have mother's intercept and mother's slope, okay, and those are correlated, and they're also correlated with father's intercept and father's slope. And so we could run this model to try and understand how mother's and father's intercepts and slopes are correlated. If we were to bring in an additional growth curve of, say, child's intercept and slope, in this model, for example, they predict mother's intercept and slope by the child's intercept, father's intercept and slope predicted by the child's intercept, and then child's slope is predicting mother's slope and father's slope. What you want to probably not do is predict intercepts by slopes. That is, rate of change, I don't know, temporally thinking about what this means. When you have in a growth curve, that first factor loading for the growth curve is set at 0. And then, so essentially you're taking information from later time points and then going back and predicting an intercept. As I say this, I realize it could be possible that you're substantively interested in that question. But most of the time, you're not going to see that. You're going to see slopes predicting slopes, intercepts predicting slopes, but you're not going to predict intercepts by slopes. Okay, I mentioned these child slopes predicting mother and father slopes. We have, Liederman and Macho have presented a common fate model. And in this case, this is an alternative to an associative growth curve model. So let's say you have husband and wife data, and where those responses from husbands and wives are highly correlated, say above 0.4, I believe is the cutoff that Liederman suggests. But if they're correlated a good amount, then you could put, say, husband and wife observed variables on the same latent variable. And what this would do then is it would represent what is common or what is correlated among husbands and wives. So this variable right here would represent what is common among husbands and wives report on this construct. And then their error terms would be what is unique to that spouse. And here we have these correlated across different time points. If you have just a common fate variable not within a growth curve, you could actually use these unique aspects of a measure as a predictor and as an outcome. Or as an outcome, and the latent variable becomes what is common or shared information, what overlap there is based on correlations. So this is another option. Another fancy option to looking at things that change longitudinally over time with multiple people is the bivariate dual change score model. And okay, so when we are doing multiple growth curves in the same analysis, it's common to want to do some invariance testing, much like we did with multiple groups or multiple family members, testing measurement invariance and structural invariance, where we tested factor loadings, intercepts, and error variances, and then following measurement invariance, we could test structural invariance. With growth curves, there's not, unlike measurement invariance where you follow these steps of we do factor loadings first, then intercepts, then error variances. With growth curves, we don't necessarily go in a specific order and stop if we don't find invariance at one place. We can test each of these separately. So one of the tests that we could test is, do we have the same slope functions? And this is usually implied. It's usually a given, because let's say that I give a survey to a husband and wife on the same day, okay? And I do that each time I measure in my study, then they're going to have the same slope function. But if for some reason let's say wives took it in February and husbands took it in May, then of every year, I guess you could have, well, even then, if they were spaced the same way, you might still have the same slope function. But at any rate, the factor loadings for the slope, as long as those are the same across both growth curves, then you have equality of slope functions. But it's possible that you don't have that at some point. Once that's established, we could look at the equality of the slope and intercept means. So is the average intercept and the average slope the same? And to me, I guess these are two different tests. Are the intercepts the same across the groups? Are the slopes the same across the groups? We can also test the variance parameters. Does the intercept variance, is it the same across groups? How about the slope variance? Is it the same across groups? And we can test that. And then we can test observed variable error variances and covariances across groups. Okay, so I say here on this slide so checking the slope functions across groups is, I think, necessary before you would equate intercept and slopes. So I think that would need to be established before you check intercept and slope means and variances. And I definitely think that intercept and slope means and variances, if those are different, then I don't know why you would test error variances and covariances across the groups. I suppose you could, but I would probably go in this order and not do the error variances if the slope factor means and variances weren't there. In fact, really what's going to be substantive for a paper is, are the intercept and slope means and variances the same or different. That's really the main thing you're going to be looking for and wanting to report in a manuscript. Okay, let me show a couple examples of adding time invariant and time varying predictors. This diagram here shows an intercept and a slope with 4 time points for y, and x1 and x2 represent time invariant covariates because they stay the same across all time points. They don't change across time. So x1 predicts the intercept and slope, and x2 predicts the intercept and slope. Now A 31 through 34 represent time varying covariates where we're predicting y11 with A31 and y12 with A32, y13 with A33, and y14 with A34. So this is how you would model time varying covariates. And in our M+ syntax it would look something like this. Let me share an example of this from what it might look like in Amos. This gets kind of messy, but you see an observed variable here across 1, 2, 3, 4, 5 time points predicting part of the growth curve for the wife, part of the growth curve for the husband. Here's the husband intercept and slope, the wife intercept and slope, a couple of time invariant predictors, and then these are our observed variables as part of the growth curve for husbands and for wives. And because these are husbands and wives, we're going to correlate the slope error terms and the intercept error terms. You can't see very well because it's kind of messy in there. But we also have these error terms for our observed variables that are part of our growth curve correlated across husband and wife. We may not be interested in interpreting this covariance between a husband and a wife error term on one of their observed variables. However, because of the non-independence between husband and wife, it's really important to include that in your model. If you don't include that in your model would be wrong. And most of the time, you'll see your model fit improves when you include those in your model. Okay, this is that model with time invariant predictors with the time varying predictors taken out. Okay, so I'm gonna set some of these up in Amos and M+. First, I'm gonna go to Amos, and what I have here is an intercept and slope for marital quality for girls and for boys. This is in a sample that is not where they are not married to each other. So we can do this. So we have an intercept mean for girls, intercept variance for girls here on the latent variable for intercept and for slope. Slope mean, slope variance. And for boys, this is our growth curve where we just have different labels. And what we would do in Amos here is we would set up in our default model. This is where nothing is constrained to be equal. Then I've got my intercept variance and my slope variance across boys and girls constrained to be equal. In the next model, then latent means constrained to be equal across boys and girls. And last, error variances constrained to be equal. And then I have a model that has all of those constraints. So the way that we would do this in terms of the order is we're going to test each of these three against the default, and if none of them are different, then we'll look at the all constraints. And so run this model, and I get the initial OK here in my output window. I'm going to go to my text output to okay, so just scrolling down here, notice we have 10 degrees of freedom, minimum was achieved. These are both good things to see. Because we have multiple groups set up, we're going to see our boys default model first. Actually, I'm just going to skip down here to model fit. This is the order I would normally go in, where I'm going to see, actually we could look at our chi-square with degrees of freedom, number of parameters. We have 19, then with 2 degrees of freedom difference it jumps up to 37, then 113 with no degrees of freedom difference, because here we've got our latent variances constrained, and then our latent variances are freed, and our latent means are constrained, and then our error variances are constrained, which we've got 4 of those, and so we have a little bit different degrees of freedom. Model fit looks, well, pretty good. It's definitely highest here in the default model. Goes down a little bit when latent variances are constrained, goes down quite a bit when latent means are constrained, and then when error variances are constrained it's down even a little bit, and all constraints down quite a bit there. Okay, might also look at our RMSEA and where we see a similar trend. Okay, so where this is going to be for, we can use these buttons down here at the bottom left to navigate our output. And so now I clicked on estimates and boys is highlighted in the default model. Let's check the latent variances constrained. Now actually we'd use this model fit to determine which model to go with, and based on this, let's see, we have model, nested model comparisons down at the bottom. The latent variances constrained model is significantly different from the default model. The latent means constrained model is definitely different from the default model. The error variances constrained is definitely different, and the all constraints is different. If we were to compare these other models, it looks like they're all different as well. So we actually, in this specific model, cannot constrain any of these parameters to be equal without worsening the model fit. So in this particular model, we would go with the output for the default model, and so we could go to the estimates for the default model, and we could scroll down here and see that the mean for boys is 4.85, and the mean, that's going to be the mean intercept, and the mean slope is not different from 0. Covariance between the intercept and slope is negative and significant, and then we have a significant amount of variation in the intercept and the slope. Let's see. This is our output then for the girls, where we have 5.625. Looks a little like a higher intercept, which is why they couldn't be constrained to be equal. The slope is not different from 0. And then we have a significant amount of variance around the intercept and slope. Okay, so we would go with this model, and then we would add in our predictors. I'm not going to add in predictors here in Amos, but the way that we would do that is we would simply, well, actually, why don't I just go ahead and do a couple. If we're going to add a predictor, we've got to add an error term to the intercept, an error term to the slope, and we can then correlate those. And we could grab our variables here, and for our time invariant predictors, we could say, well, let's see, whoops, actually, because we're looking at boys and girls, I don't think that gender is one to look at, but number of years married, we could use that. Okay, and so we could take this and predict the intercept. Okay, because I have the variance parameter constrained, Amos draws up a flag on this one. We're going to say remove the constraint on the variance and draw the arrow. And I'll do the same for slope. It's going to raise the same issue. The problem is that now where our latent variances are constrained, it's not going to understand that. What I'm going to do here is just I'm going to keep that model in here because we want to know that, but instead I'm going to pull up the latent residual for that latent variable, and in that variance I'm going to put the intercept variance for, let's see, this model is for boys, and then this one would be the slope variance for boys, and then we could click on girls. Okay, just make sure that we did that. No, I don't know why, but it's not letting those differ across groups. So if we go to interface properties to miscellaneous, we have to allow the different path diagrams to be different for different groups. Okay, and now this is going to be for boys, and this one is going to be for boys, and this one will be for girls. Okay, so I think now we're good to go. Oh, I've got to name those unobserved variables. Okay. Oh, it still thinks that, I see, so for girls, I've got to unconstrain the variance parameters here. Now the mean, we're okay, it's the variance that is the problem. And not sure why we're not getting a variance here. So for the boys, we don't have the variance labeled. For the girls, maybe if So with our time varying predictor in the model, we could then, looks like the model did run, our model fit looks okay, and we're going to go with the default model. And so if I go to the output for a default model, we can see that for our regression weights, that years married is not significantly related to our intercept or our slope for boys, and not related to intercept for girls, and trend level related to slope for girls. Okay, so I'm going to go ahead and close up Amos here and pull up a couple of different examples. All right, so in M+, let me just show a couple of models here. Okay, this model is a growth curve of latent variables. And so what we have here is some latent variables, grandparent closeness at time 2, 3, and 4. And then in order for this model to run, you'll see that the factor loadings are constrained to be equal across those time points, and the intercepts are constrained to be equal across those time points, and then the error variances are also constrained to be equal across those time points, and I've constrained the mean of the latent variables to be 0. And then here's my growth curve right here. GP int, GP slope line with GP 2, 3, and 4 at 0, 1, and 2. And then I've got family structure predicting the intercept and slope, and I also have a plot of that line, which is one thing that's nice about M+, is that it will actually plot your data. I'm just going to show the diagram here so you get a sense of what this model looks like. Except for that I don't see a model here. So maybe there was a problem with that. Let's try it one more time. Okay, doesn't seem to want to come up. I could look at a plot of estimated means where we have our y going down across time. Something about that didn't look quite right. It looked a little steep, but we can pull it up with one of our other models. So that's how you would run a latent variable growth curve. Let's see. This is our latent variable growth curve input. And here is what our observed variable growth curve would look like with the same model. And in fact, let's just run this just out of curiosity to look at that plot of estimated means, and not quite as steep. That other one was a little steep, so I might want to go back and check that and see if I've got an error in my syntax. It's always a good idea to look at plots and compare that with your output. See how it matches up there. You shouldn't find any surprises. Okay, and now this example has a regular observed variable growth curve. Here's our means and intercepts to deal with missing data. Here's a growth curve for the wife intercept and wife slope, and we're looking at 0, 1, 2, 3, 4, 5, and 6 across 6 time points. And here's the husband's intercept across 6 time points. And then we have these time invariant covariates of income, number of children, race, health risk, and those are predicting the intercept and slope. And then we have some time varying predictors of depression. So wife's depression at time 1 predicting wife's marital quality at time 1, and so forth through time 5, and then for husbands through time 5. We also have a plot for each of those. And if I run this, I'm going to show briefly the diagram. Although it's a little messy, you can see here's the wife's intercept and slope, and then here's some time invariant covariates. If I scroll down, here's the husband's intercept and slope, and then this is one of the time varying covariates. So this is at time 5 for husbands and time 5 for wives. This one I would probably put up a little bit. Whoops. You could see, kind of put it next to the, so here's the predictor and here's the outcome. So you get a sense, these models get a little complicated. When we look at the output, there's actually a pretty stark trend here. If we start here with our model estimation terminated normally, we have model fit that is okay, RMSEA 0.05, CFI 0.91. That's a little low. Here we have, starting right here, our predictors. So our time invariant predictors right here, with a couple of them predicting wife's intercept and race predicting wife slope. For husband's intercept, we've got income, and that's about it. And then down here, we have these time varying covariates. So wife's depression predicting wife's marital quality at time 1, time 2, time 3, time 4, time 5, and then husband's time 1, 2, 3, 4, 5. Notice all of these coefficients are in the same direction and they're all statistically significant, suggesting that depression has a significant association with marital quality at each time point. And this might make me think that this would be a better way to model this data. The model fit is a little concerning to me, so I'd want to go back in and see, what might be going on with the model that might be decreasing that CFI. But otherwise, this suggests an interesting trend in the results. So we can model, it's a good idea to build these models small and get bigger. So you start with a growth curve for one person, figure that one out, then do a growth curve for the other person separately, figure that one out, then correlate intercepts and slopes, then add time invariant predictors of intercept and slope, and last time varying predictors of each time point. And you can answer really interesting questions when you put growth curves together, and you can test whether the means and intercepts are the same across these. You can do it within the same group, across the same group, across different groups. You can test the variances, and then you can model error variances to see if those differ as well. These models can get very complex and take a little bit longer to run, so prepare yourselves for a little bit of work if you are going to publish one of these models. But they can answer really interesting questions, and a lot of times we see that growth occurs is like with the life course theory, we see linked lives where husbands and wives' trajectories they influence each other, and same with parents and children and other types of relationships. So good luck with these kinds of models, and I hope you found this helpful.